Hello AP Chemistry and welcome to Chapter 19, which is the last half of our thermodynamics chapter or unit, right, which covers chapters 5 and 19 together, right? So just heads up, there are certain topics in Chapter 19 that we will sort of gloss over, right, because obviously we've skipped a few chapters in between, right, and so those topics will get revisited again when we get to the pertinent topics. So don't worry if some of the things are fuzzy, and I'll point out which things are okay to be fuzzy as we encounter them. All right, so anyway, Chapter 19, Thermodynamics. We spent all of Chapter 5 basically figuring out what is enthalpy, and then what are the different ways we can either experimentally determine or calculate enthalpy, which is the amount of thermal energy exchanged during the course of a process, right? Now in Chapter 19, we introduce a new concept called entropy, okay? Where entropy is, right, you will never say randomness, because randomness is not going to earn you a point on the AP Chemistry exam, right? You will say something along the lines of degrees of freedom, total number of microstates available to the sample. And microstates is good because we can always talk about the types of motion, thus the number of microstates, and therefore the entropy, okay? So you're never going to write down, anything less than that. All right, so first, before we get there, entropy, things to think about, right? So one, we have this word spontaneous, right? Where spontaneous simply means that it happens without outside intervention, right? Nothing has to happen to it for whatever it is to happen, right? As in, if you open your hand, these eggs will fall down. That is spontaneous, right? And they don't magically go back up to your hand. That's not a thing, right? Likewise here, if we have a gas trapped at 1 atmosphere with a closed stopcock, and that's just like on the burettes, right? It's something that basically plugs the space in between there, right? Once we open that up, right, spontaneous means, in this case, that gas is going to spread out to fill both chambers, right? And it's deciding it's all moving back into one chamber, not spontaneous, not going to happen, right? And so there are a lot of processes where that's true, where one direction absolutely happens and the reverse direction does not happen. Then there are ones that are temperature dependent, like water, right? The melting and freezing of water, where it is spontaneous, meaning it happens without outside intervention, depending on the temperature, right? So it can be sometimes, right? Which then brings us to a few of the takeaway points from the first section of Chapter 19, right? Which is that irreversible processes are spontaneous, right? If it cannot go the other way, right, then it is spontaneous, okay? If it is irreversible, right, that means it leads to an increase in total entropy, okay? Which then brings us to the simple statement that entropy of the universe increases in any spontaneous process, right? Which is the second law of thermodynamics, and not something that you're expected to be able to calculate the entropy of the universe, right? We're going to talk a little bit more about where some of the quantitative work comes in, right? But just know that if something is spontaneous, right, it's because it increases the entropy of the universe, okay? Ways to talk about entropy, right? So one, we've got this equation from Boltzmann, right, where this is the number of microstates, W represents the number of microstates, and it is directly proportional to entropy. Yes, number of microstates is directly proportional to entropy. That's the whole point of that equation, and that's the extent to which you need to know it, right? And so again, entropy is based on types of motions, right? So we can have vibrations, right, where atoms within a molecule can change their distance or arrangement to that or a relationship to that molecule, right? In that this bond, right, these two atoms can move closer together or further apart, right? These two atoms can move closer together or further apart, right? And those are types of vibrations, right? Rotation simply means, like, if we think about a fixed point of rotation, right, it can spin in one direction or spin in the other without moving. And then obviously there's the concept of translational motion, where it can literally just move to wherever. Yes, it can literally cross space and move, right? All right. And in terms of entropy, one of the other ways to look at it, right, is looking at different states, right? If we think about water, right, we have solid water, where we have a rigid crystalline structure, right? in that it can vibrate only, right, because it's fixed in position relative to its neighbors, right? That's the literal definition of a solid, right? Whereas once it melts to become a liquid, right, we now have translational motion, right, along with the vibrational and rotational motion, right? So again, we've increased the types of motion, thus an increase in entropy, right? When it becomes water vapor, right, then we have complete freedom for translation, right? In that it's no longer stuck adjacent to its neighbor, right? But there is so much kinetic energy, right? Like we talked about last year, so much kinetic energy, no attractions between the molecules, right? So complete translational motion. So increase in entropy, yes? So obviously entropy is also tied to temperature, right? Which makes sense because we just talked about how the state matters there, right? So if it's a higher temperature, there's more entropy because there's more kinetic energy, which means there are more microstates. And we can think of microstates as also being like an instantaneous snapshot of a sample, right? If there is a higher temperature, thus more kinetic energy, there are simply more ways for it to be arranged, right? Going back to your guys' outline, I did include a picture of a Maxwell-Boltzmann energy distribution, right? In that at higher temperatures, what we also end up with, right, is that even over a set of just atoms, for example, like helium atoms or something, right? If we increase the temperature, we end up with a greater average kinetic energy, which ends up, the way that plays out is that there are a wider range of speeds, molecular speeds or atomic speeds for the particles, right? And that broader distribution of energy is also a way to describe entropy, right? And then we've got molecular complexity, right? So something that has 2 atoms versus something that is composed of 10 atoms, right? The thing with 10 atoms has more molecular complexity. That means there's more of that vibrational motion that can happen, which means that that molecule just innately has a higher entropy, okay? And then that other law of thermodynamics that says entropy equals 0 when? That's right, at 0 Kelvin. So then, evaluating the entropy of a process, right? Let's do this one first. So if we have this reaction, which says that we have some NO gas plus oxygen gas produces NO2 gas, we might wonder, well, how can we evaluate the entropy of a process, right? If the temperature stays the same, what are we supposed to do, right? They're in the same flask, so they're in the same amount of space, right? That's not changing, right? Then we have to look at what else is there, right? So here it says that we have 2 moles of gas and 1 mole of gas, so 3 moles of gas. And over here we only have 2 moles of gas, right? Which means we have a decrease in entropy. Yes? Does that make sense? Okay. In that anytime we decrease the number of moles of gas present, that is a decrease in entropy. Here we have the dissolving of an ionic compound in water, right? And here what we need to think about, right? So if we go back, right, liquid water doesn't have much organization, right? The molecules can all move wherever they want to relative to their neighbors, right? As long as they stay stuck to their neighbors. Once we introduce ions, right, then we get a very direction-specific arrangement, right? Because going back to the fact that water is polar, right, it has a positive and a negative end, and it forms these hydration shells around each of those ions, which means that as we dissolve that ionic solid, more order is imparted to the water, right? The water is more ordered than it was before. It has fewer microstates. For the ionic compound, though, the ionic compound now has translational motion, and so it has far more motion and far more entropy, right? And so deciding the entropy of dissolving is not something you can just, say, right? It's something where we would need some evidence or we would need some other pieces of information, right? And we'll look at some examples of that later, right? But just know that, like we talked about before with enthalpy, right? There's the enthalpy of the products and the reactants that we have to think about, right? Because there are 2 things happening, right? One thing happens on the reactant side and another thing on the product side, right? And likewise here, right? We've got multiple things happening. So deciding the entropy of the whole process means we have to be able to put all those pieces together. And if we don't have numbers for that, we can't speculate that the entropy of dissolving is either positive or negative. Yes? All right. Fantastic. All right, so let's do some predicting. So these are the practices from, I think, 19.2. or 3, I'm not sure. All right, so indicate whether each process produces an increase or decrease in the entropy of the system. And so again, system in this case is going to be our reaction, right, or the thing that we're looking at or talking about. If we go from CO solid to CO gas, obviously that is an increase in entropy, yes? If we have CaO solid, CO2 gas to CaO solid, definite decrease in entropy, right, because we had 1 mole of gas. Now we have no moles of gas. We have decreased the translational motion, right? We have gas, solid, definite decrease in entropy, right? Here we have gas, then we have to go do a mole count. So this is 3 moles of gas versus 2 moles of gas, which means this is also a decrease in entropy, okay? Next one says to choose the system with the greater entropy, right? So keeping all those things in mind again, right? If we have 1 mole of H2 at STP versus 1 mole of H2 at 100 and half an atmosphere, right? So STP, if we think back, what is that? Right? That's 0 degrees Celsius and 1 atmosphere, right? When we talk about standard for gases. And here we have higher temp, and we said higher temperature, more kinetic energy, right? More microstates, right? And half an atmosphere. And if we think about how to, like what that means, right? So it's still 1 mole of gas. And if it's 1 mole of gas at a lower pressure, that's another way of saying, so lower pressure is always, often goes hand in hand with a greater volume, right? Which means that we have, that hydrogen now has more volume to be in, right? Like a greater amount of space that it is allowed to occupy, right? So between having higher temperature, which I half erased, that's okay, and a greater volume to be in, right? This one is the greater entropy, yes? Higher entropy goes to that second sample. All right, next up it says we have 1 mole of water at 0 or 1 mole of liquid water at 25. This one's definitely that liquid water, right? Liquid has more, liquid has translational motion, which solid does not have, in addition to the higher temperature. 1 mole of hydrogen at STP or 1 mole of SO2 gas at STP. So they have the same temperature, same pressure, right? So that's not a thing. They have the same amount of gas molecules. So here it's going to come down to molecular complexity, right? And that SO2 has more atoms. Because it has more atoms, right, there are more options for vibrational motion, right, which means that one has higher entropy. 1 mole of N2O4 versus 2 moles of NO2. Yep. It's going to be the sample that has more molecules because, again, right, microstates being an instantaneous snapshot of what's happening. If there are literally more particles, then there are more options for how those particles are arranged. Yeah? All right. Thank you for listening. Be good. And in the next one, we will talk more about entropy and some quantitative aspects. All right. Thanks for listening. Be good. See you soon. Bye.